Hello there. Welcome to tonight's journey, where your imagination can roam even while you rest. You've found yourself in a quiet space, perhaps curled up under blankets, the glow of your screen or speaker casting a small halo around you. Before we begin, pause and notice, where are you right now? Is it late, with the world hushed around you, or is it earlier, with the hum of life still carrying through your window? Whatever the hour, I'm glad you're here. If you'd like, share that place and time in the comments below. And while you're at it, consider giving a gentle tap to like and subscribe. Those small acts help keep these bedtime stories drifting onward to others who, like you, wander towards sleep by way of curiosity. Now, let's set our scene together. Tonight's story carries us vertically, not just sideways across maps of stars, but up and down, into the overlooked directions, what lies above the solar system and what waits below it. Most of us are used to thinking outward, what planets orbit nearby, what galaxies lie across vast distances. But tonight we tilt the axis 90 degrees. Picture the great plain of the Milky Way as if it were a sprawling record spinning, and our solar system set into its grooves. Now imagine lifting yourself above that record, or diving below it. What do you see? What forces guide you? And how do scientists even decide what counts as up and down when there is no universal ceiling or floor in space? That's the vertical question, and it may surprise you with both its clarity and its strangeness. Astronomers do define north and south for our galaxy, not unlike how sailors once fixed north and south across Earth's oceans. The difference, of course, is that Earth's poles are defined by its spin and magnetic fields, whereas the Milky Way's poles are defined by a flattened disk of billions of stars. Galactic north points toward the constellation Coma Berenices, a faint cluster of stars once mythically tied to the locks of an Egyptian queen's hair. Galactic south points the opposite way, into Sculptor, a more subdued southern sky constellation known for its scattering of faint galaxies. You probably won't survive a trip to either pole. After all, traveling hundreds or thousands of light years beyond our protective bubble would expose you to unimaginable radiation. But imagining the view lets you climb beyond the solar system's shell in perfect safety. As you picture this, feel the story's rhythm. It moves like breath, in and out, upward and downward. Think of yourself slowly rising above a spinning silvery disk. The Milky Way beneath you stretches flat, its river of stars smeared across black. Below, if you drop instead, you would fall into shadows lined with the faintest, most delicate galaxies seen through Sculptor's Window. Astronomers call these openings clean windows because dust and gas that usually block our line of sight thin out here. Imagine sitting at the edge of a dimly lit room where, for a moment, the curtains part and you glimpse far beyond. That is what makes these vertical views so precious. But before we drift too far into quiet starlight, let's plant a bit of earthly grounding. A historical fact: in 1958, the International Astronomical Union formally established the Galactic Coordinate System, defining the Milky Way's plane, its zero longitude, and its poles. Before then, astronomers used scattered reference points, stars, clusters, the visible arch of the galaxy, without a unified frame. The adoption of galactic north and south gave scientists a shared compass, one they could return to across decades of research, not unlike how seafarers once agreed on celestial navigation by Polaris in the northern sky. Now, for a quirk that blends myth with measurement, the naming of Coma Berenices, the direction of galactic north, carries with it an ancient story. Queen Berenice II of Egypt is said to have cut off her hair as an offering to the gods, placing it in a temple. When the hair went missing, the court astronomer declared that it had been carried to the heavens, now immortal as a faint scattering of stars. Who could have guessed that millennia later, scientists would point telescopes through this very patch of sky to define the universe's northward axis? A playful myth laced into the backbone of modern astronomy. And as for debates, well, scientists still argue whether defining a galactic north and south is anything more than convenience. After all, in the grand scheme, directions are relative. From the perspective of a galaxy billions of light years away, our north is meaningless, just another angle on a spinning spiral. Some astrophysicists treat the labels as merely useful scaffolding for surveys and maps, while others suggest they reveal deeper symmetries in galactic dynamics, like the orientation of magnetic fields or the shaping of cosmic rays. You hear the whisper of disagreement even in the most seemingly objective labels. Picture yourself floating there now, just a few light years above the galactic plane. The solar system is a tiny dot behind you, hidden within swirling gas and dust. Below you stretches a gauzy mist, the interstellar medium, woven with filaments and clouds. Above you arch the great fountains of radiation and magnetic fields that spill out of the Milky Way's disk like luminous tides. You hover in the in-between, your perspective widened. North and south cease to be directions of Earth and become gateways into entirely new layers of cosmic structure. The soothing hum of the galaxy rises around you like a soft chord, the combined light of billions of stars blending into a single glow. You drift, unhurried. You can almost feel the weight of history here, the centuries of stargazers who looked up and wondered, the astronomers who charted maps by hand, the modern satellites that beam down torrents of data. Above and below are not abstract, they are chosen, deliberate lenses through which humans have learned to see order in the ungraspable vastness. And so, the vertical question carries us forward: what exists above and below the solar system? To answer that, we will glide outward step by step from quiet southern windows, to the fierce polar winds, to the cosmic rays, to the towering bubbles of gamma light, and finally to the strange anomalies that still perplex us. You will not need to survive the journey in body, you only need to travel in imagination, carried by the slow rhythm of this voice until your eyelids soften and dreams rise. You're already adrift in the vertical frame of the galaxy, floating in your mind above and below the solar system. And now it's time to ask, how do we even draw the map? On Earth, you know north and south, because compasses swing, poles pull, and globes sit neatly tilted on axes. In space, though, there is no up, no down, no compass needle. Astronomers had to invent one. They call it the Galactic Coordinate System, a scaffolding of imaginary lines draped across the sky like invisible longitude and latitude. Close your eyes for a moment. Imagine the Milky Way's glowing band arched over you like a river of powdered silver. That river is the galaxy's plane, a thin but sprawling disk of stars, dust, and gas. If you could slice it like a record, you'd find that most of its light, most of its drama, happens close to the groove. And then picture turning the record on edge. From that thin disk, you can define two poles, one straight up, one straight down. North points to the constellation Coma Berenices, south to Sculptor, and with that the map is born. The act of choosing directions may sound trivial, but it changed astronomy. A historical note in 1932, the Dutch astronomer Jan Hendrik Oort suggested a system aligned to the Milky Way, allowing astronomers to measure positions relative to the galactic plane. This was refined and officially adopted in 1958 by the International Astronomical Union, a moment that gave scientists worldwide a shared sky compass. No longer was the cosmos oriented by Earth's quirks alone, it now had its own galactic grid. Think of how seafarers once used sextants to chart their way across oceans. The Galactic Coordinate System is the astronomer's sextant, allowing observations to be catalogued not in relation to the tilt of Earth's axis, but to the tilt of the galaxy itself. Without this, surveys like the Sloan Digital Sky Survey or the 2-degree field galaxy redshift survey would have been a jigsaw puzzle of mismatched directions. With it, the puzzle pieces click into place. But here comes a quirk you might not expect. When astronomers say galactic north, they mean the pole that lines up with Earth's north celestial hemisphere. In other words, the decision was partly arbitrary, tied to our own vantage point. If a civilization in Andromeda drew its own coordinate grid, its north might be our south. You can almost imagine two astronomers across galaxies holding up star maps to each other, shaking their heads at the mismatched compasses. The labels are ours, a reminder that cosmic order is as much human invention as it is discovery, and debates remain. Scientists still argue whether this coordinate system reveals genuine features or is simply a convenient convention. Some suggest the poles align with deeper galactic phenomena, large-scale magnetic field lines, cosmic ray flows, or asymmetries in star distributions. Others insist it's only geometry, useful for maps but devoid of cosmic meaning. The very act of calling something north tempts us into believing it has some objective truth. But in space, truth is often a matter of frame. Now let yourself imagine the grid itself. Picture a transparent sphere encasing Earth, etched with longitudes that run parallel to the galaxy's plane. A line at 0 degrees longitude pierces the bright bulge of Sagittarius, the center of the Milky Way. From there, longitudes radiate outward, wrapping the whole sky. Latitudes stretch above and below the plane, climbing toward +90 at the galactic North Pole and -90 at the galactic South. With each coordinate, astronomers pin stars, nebulae, and galaxies in place, transforming the chaos of glittering dots into an ordered atlas. The power of this system emerges when you think about how astronomers search for faint galaxies. Dust in the Milky Way often obscures their view, clouding the sky with dark bands that swallow distant light. But by moving toward the poles, where the disk grows thinner, the view clears. The galactic plane is noisy, like a crowded marketplace. The poles are quiet lanes leading to distant horizons. That clarity explains why so many deep sky surveys favor the polar regions. Without this system, knowing where to look would be like wandering blindfolded through a forest. Pause here and breathe with the thought of that clarity. The grid is human-made, yet it reveals something deeply natural, that the Milky Way itself is a flattened disk, and that its poles give us an escape route for sight. Upward into Coma Berenices, downward into Sculptor, those are the clean windows. Through them, light streams from galaxies billions of years old, carrying whispers of the early universe. For a historical curiosity, when William Herschel, in the late 18th century, first tried to map the shape of the Milky Way, he did so without this coordinate system. He counted stars across patches of sky, assuming brightness equaled depth. His maps produced a lopsided, oddly carrot-shaped galaxy. The flaw wasn't his math, but his missing compass. Dust dimmed his view, skewing his counts. Only with the galactic coordinates, and later infrared astronomy, did the galaxy's true disk shape become visible. Herschel's carrot became the spiral we know today. And here's a fringe tidbit, something that sounds like it belongs more in science fiction than astrophysics. Some astronomers have mused about defining galactic coordinates, not by stars at all, but by the mysterious flows of dark matter. Since dark matter outweighs normal matter, shouldn't its distribution define up and down more truly than our visible disk? It's speculative and still far from measurable, but the idea reminds us that even our maps may someday be redrawn in unseen ink. Think again of yourself drifting in space. You see no lines, no latitudes or longitudes. The grid is invisible, a projection only our minds carry. And yet, thanks to it, we can tell stories that stretch across the universe. We can say the Fermi Bubbles rise tens of thousands of light years above the plane. We can note that the cold spot anomaly glows from the southern sky. We can point, quite literally, to directions of wonder. All the while, the debate hums, are we uncovering truths, or simply arranging them in ways that suit our earth-born imaginations? You can rest easy though, knowing that both might be true. The coordinates are human, but the stars they chart are not. That tension, that mix of invention and discovery, is what makes astronomy a uniquely human craft. The solar system spins on within this map, like a bead carried on the turntable of the galaxy. You hover above it now, watching as Earth's orbit scribbles circles, as Jupiter traces loops, as the Sun drifts slowly along its galactic path. Beneath you, Coma Berenices opens its quiet patch of sky. Below you, Sculptor waits, clear and still. The map is drawn, the compass set. From here, our story can flow into the windows themselves, and what they reveal when you peer beyond the dust. Drifting now along the invisible lines of the galactic grid, you find yourself lowering toward the south. Beneath the solar system lies Sculptor, a dim constellation not known for bright stars but treasured for the spaces between them. Here, the galactic plane thins. Dust, usually so thick and suffocating, fades to a whisper. The sky becomes translucent. Astronomers call this a window, and it is through this southern window that some of our most important surveys have peered outward. You can picture it like standing on the shore of a foggy lake. Most directions are blurred, muffled by mist, But one patch clears, and through it you glimpse distant mountains, sharper than anything else around. Sculptor is that clearing in the fog of the Milky Way, its relative emptiness is not a loss but a gift, an opening for sight. A historical fact anchors this view. In the late 1990s and early 2000s, astronomers launched the 2-degree field galaxy redshift survey, known simply as 2DFGRS. They chose Sculptor's southern pole because the window's clarity meant they could gather deep spectra of galaxies without dust interfering. Over 200,000 galaxies were measured, their redshifts mapped, creating one of the first 3-dimensional atlases of the universe. Imagine, line by line, measuring the fingerprints of starlight, and then stacking those fingerprints until a vast cosmic web emerged. Without Sculptor's window, such a survey would have been tangled in obscuration. Now let's pause for a quirk, one that lingers on the edge of science and myth. The Sculptor constellation itself was not an ancient figure from mythology like Orion or Hercules. Instead, it was invented in the 18th century by the French astronomer Nicolas Louis de Lacaille, who filled the southern skies with new constellations during his time observing at the Cape of Good Hope. He named it Apparatus Sculptoris, the sculptor's studio, complete with imagined tools, a playful, earthly nod in a sky that otherwise tells stories of gods and monsters. Today, this constellation, born of art rather than myth, serves as a keyhole to the farthest reaches of space. And yet, debates weave even here. Scientists still argue whether Sculptor's clarity is uniform or if subtle veils of dust remain, distorting what we see. Modern infrared maps show faint strands of gas even in supposedly clear zones. Some suggest these hidden veils could bias surveys, slightly altering our understanding of the distribution of galaxies. Is the window perfectly clean, or only relatively so? The argument remains open, reminding us that even the clearest glass might have smudges when inspected closely enough. For you, drifting in thought, the Sculptor window is a breathtaking sight. Through it, galaxies glow in layers, scattered like distant lanterns across a black sea. Some are close spirals, arms curling delicately. Others are faint smudges billions of light years away. Light from those galaxies left when Earth's earliest continents were still barren, when life clung only to oceans. The photons have traveled unbroken, slipping through Sculptor's corridor to meet your gaze now. Close your eyes and imagine the soundscape. There is a hush here, quieter than the galactic plane. Fewer stars, fewer interstellar clouds. The silence feels like a deep exhale, as if the galaxy itself pauses. Against that silence, the pulse of data collection rings faintly, spectrographs splitting light into rainbow bands, redshift lines shifting, telescopes whirring gently as they reposition. Each sound is delicate, precise, like a sculptor tapping chisel to stone, fitting for a constellation named after a workshop. Remember William Herschel, counting stars by hand centuries before. If only he had pointed through Sculptor's patch, his counts might have revealed a very different structure. Instead, his maps filled with dust-obscured false thickness. It took surveys like 2DFGRS, anchored in Sculptor's clarity, to untangle those errors. This is the quiet irony. Sometimes the best discoveries come, not from the brightest, busiest parts of the sky, but from the overlooked corners where less blocks your view. And for a fringe tidbit, some cosmologists have speculated that the Sculptor window, by sheer chance, might line up with cosmic anomalies. A few suggested that gravitational waves still faintly detected might propagate more easily through such low-density corridors. Others playfully muse that if we were ever to send probes far beyond the solar system, a southern trajectory might yield the cleanest escape path, free of clutter. None of this is confirmed, of course, but the speculation reveals how astronomers dream beyond their data. Scientists still argue whether focusing so heavily on windows like Sculptor biases our cosmic maps. After all, if you mostly look where the sky is clear, do you miss the hidden structures buried behind dust elsewhere? It is as if a cartographer drew a map of Earth's rivers only in places where the weather was good. The debate continues, shaping how future surveys like the Vera Rubin Observatory's Legacy Survey of Space and Time balance coverage between easy windows and dust-heavy regions. As you drift, you recall the grid we traced earlier. Galactic South is not just a label, it is a vantage point, and through it you can gaze far beyond the Milky Way. You are peering into cosmic time, your eyes tracing filaments of the large-scale structure. Imagine the galaxies clustering into walls and knots, voids yawning between them. Sculptor is not empty at all. It is the door through which the fullness of the universe is seen. The scene softens as you float lower. The solar system glimmers faintly above you now, just a speck set against the Milky Way's plane. Below, through Sculptor's corridor, the universe stretches nearly infinite. Your breathing slows. You sense that this window is not just about astronomy, but about perception itself. Sometimes clarity comes not from adding more light, but from finding where shadows thin. That's the lesson Sculptor whispers to you as you drift, gently falling, yet perfectly at rest. From the southern quiet you now turn, rising back through the solar system, not toward Sculptor's empty corridor, but toward the north, toward the corridor carved above the sun's poles. Here the airless dark grows alive with streaming particles, a place where our star breathes outward in constant invisible wind. You feel yourself gliding along that current, lifted as if on a tide. The solar system is not wrapped in silence, it exhales, and those exhalations shape the very boundary between our world and interstellar space. Astronomers call it the solar wind, a stream of charged particles, mostly protons and electrons, that pours from the sun in every direction. Close to the plane of the planets, this wind is turbulent, gusting with storms, carrying the echo of sunspots and flares. But high above the poles it behaves differently. It flows faster, smoother, steadier, like clear water compared to a frothing sea. This discovery belongs to a spacecraft with a quiet, mythic name, Ulysses. A historical note. In 1990, Ulysses launched aboard the Space Shuttle Discovery, carried first toward Jupiter, and then swung into a long polar orbit of the Sun. For nearly 2 decades it traced arcs above and below the solar poles, a path no other spacecraft had taken. Its data transformed our picture of the Sun's wind. Where the equatorial wind averaged around 400 kilometers per second, the polar wind rushed at nearly 800, and it did so with remarkable constancy. Astronomers suddenly understood the poles were not only different, they were key to shaping the bubble of space around us. Imagine this bubble, the heliosphere. It surrounds the entire solar system like a cocoon, shielding us from some of the harshest cosmic rays. Its shape, once thought to be round, is now believed to be more like a teardrop, stretched by the sun's motion through the galaxy. And at its poles, the polar winds carve long corridors outward, pushing the boundary further than at the equator. You hover within one of these corridors now, drifting upward on its breath. Here's a quirk that might amuse you. Before Ulysses, scientists assumed the solar wind would behave much the same in all directions, uniform and steady. They imagined the sun as a simple fountain, spraying equally from every side. Ulysses proved otherwise. It showed that the sun is more like a dynamic artist, painting with different strokes above and below than across its middle. That unexpected contrast gave the heliosphere its texture. Without Ulysses, we might still be picturing the sun as a bland, evenly leaking ball, and debates, they flourish. Scientists still argue whether the polar wind is as steady today as Ulysses found decades ago, or whether cycles of solar magnetism alter it more than we think. The sun's magnetic field flips roughly every 11 years, dragging its wind patterns with it. Some models suggest the polar outflows surge and wane dramatically, while others hold that the constancy remains a defining trait. New probes, like Parker Solar Probe, nibble closer to these answers, but the full truth waits. As you float through this imagined polar corridor, picture the particles themselves. They stream past you like fine grains of sand, each one charged, each one tracing invisible lines of magnetic force. They are ghosts of the sun, fragments of its surface carried outward. If you held out a hand, if hands could exist here, you would feel nothing. The particles are too diffuse to touch, yet their collective force sculpts a bubble billions of kilometers wide. Such is the paradox of space, emptiness that still commands shape. The corridor hums, not with sound your ears could hear, but with the oscillations of plasma. Radio instruments aboard spacecraft record it as eerie whistles and chirps, tones that rise and fall like alien birdsong. You drift through those tones now, lulled by their rhythm, your breath sinking with their waves. the North Corridor becomes not just a scientific construct, but a lullaby of charged wind. Consider, too, the solar system seen from this vantage. Looking down, you see the planets strung like jewels along the ecliptic. Jupiter swirls with storm bands, Saturn's rings gleam, Earth shines with its blue oceans. Above them all, your corridor stretches out, invisible to eyes but real in force. This is the route Voyager 1 took, skimming close to the Sun's northern pole as it drifted outward toward the edge. In 2012, it crossed the heliopause, that boundary where solar wind yields to the interstellar medium, a historic crossing, the first human-made object to slip into the true beyond. A fringe tidbit to tickle your thoughts. Some theorists have speculated that if life exists in the outer solar system, perhaps in shielded subsurface oceans of moons like Europa, it might feel subtle influences from these polar winds. Charged particles streaming down magnetic funnels could create energy imbalances, sparking chemistry in hidden seas. It is only speculation, but it shows how far the reach of the polar corridor might extend, seeding not only space but even hidden worlds. And as always, the debates remain. Scientists still argue whether Voyager's crossing was final proof of leaving the heliosphere, or whether the boundaries are fuzzier, more like overlapping curtains. Did Voyager truly enter interstellar space, or only a transition zone where solar and galactic fields blend? The question matters, but it also delights, because it shows that even with machines billions of kilometers away, uncertainty lingers, keeping mystery alive. From where you drift now, the mystery feels soothing. You are carried on a tide you cannot feel, past particles you cannot see, within a corridor that is invisible but utterly real. The northward path stretches on, fading into black, into regions where no human body has ever traveled. You may not survive the journey in flesh, but in imagination, you are perfectly safe, perfectly calm, a voyager of the polar wind. You rise higher still, carried along the swift currents of the north polar wind until the air of the solar system thins, and then thins again, until finally the exhalation of the sun begins to falter. The corridor narrows, and the once steady stream of particles sputters. This is not a sharp wall, but a transition, a liminal place where one breath ends and another begins. You are approaching the heliopause, the edge of the sun's protective bubble. Imagine drifting here in 2012, when Voyager 1 reached this very boundary. It had traveled for 35 years, launched in 1977, looping past Jupiter and Saturn, using their gravity to fling itself outward. At last it pressed against the heliosphere's skin. Scientists waited, tense, listening. They expected a sudden shift, perhaps a neat flip in the direction of magnetic fields. Instead, what Voyager reported was stranger and gentler. The fields did not flip, they blended. The solar system's magnetic lines and the galaxies beyond them seemed to shake hands rather than clash. A historical fact sharpens this moment. Voyager's crossing marked the first time a human-made object entered interstellar space. Its tiny golden record, carrying music and greetings from Earth, slipped beyond the sun's dominion. It was as if a single bottle had been cast into the ocean of the galaxy, bearing whispers of our species. To this day, Voyager continues to send faint signals back, its power dwindling, its instruments slowly shutting down, but its presence out there undeniable. And here's a quirk to smile at. The heliopause was once imagined like the surface of a balloon, smooth and round. But data from Voyager, along with models of the sun's motion through the galaxy, revealed something else entirely. The heliosphere is lopsided, tilted, shaped like a teardrop pushed back by the interstellar wind. If you could see it, you would find it skewed, its nose pointing forward as the sun plows through space, its tail stretching behind. The solar system is not wrapped in a neat bubble, but in a windswept cloak. Debates, of course, swirl around this shape. Scientists still argue whether the heliosphere trails a long comet-like tail, or whether it is more of a blunt, rounded droplet. Some models suggest twin jets shooting from the poles, like cosmic exhaust pipes. Others insist the boundary is far more chaotic, shredded by turbulence. The truth remains elusive, stitched from fragments of data gathered by distant spacecraft and Earth-based telescopes. No one has yet seen the whole cocoon at once. As you drift here in imagination, the soundscape changes. Where once the solar wind sang in whistles and chirps, now the tones stretch into low, drawn-out hums. Voyager's instruments recorded plasma oscillations, eerie in their resonance, like the groaning of a distant cello. Through those sounds, scientists could measure the density of the surrounding interstellar medium, thicker, colder, heavier than the solar wind. You hover at that seam, one ear tuned to the sun's chorus, the other to the galaxy's deeper song. Look back behind you. Within the heliosphere, the solar system spins quietly, planets tracing their paths, comets drifting. Look outward ahead. Beyond the heliopause lies the local interstellar cloud, a faint, tenuous region of gas the sun currently passes through. This cloud is just one filament in a tangled network, a shifting fog of hydrogen and helium that stretches across space. We live within it unknowingly, like a fish within water too vast to see. And here is a fringe tidbit. Some have speculated that as the sun moves between these interstellar clouds, perhaps millions of years from now, our climate and cosmic environment could change. Passing into a denser cloud might shrink the heliosphere, letting in more cosmic rays, subtly altering Earth's atmosphere. It is an idea on the boundary of astrophysics and paleoclimatology, suggesting that even geological history might bear the fingerprints of interstellar weather. Not proven, but tantalizing. Scientists still argue whether Voyager 1 is truly in interstellar space. Some call its region interstellar, others prefer Heliothceith, a transition zone. The magnetic fields refuse to cooperate with tidy labels. Voyager 2, crossing later in 2018, reported similar puzzles. Are we in or merely brushing against the threshold? The debate itself becomes part of the story, proof that even our boldest emissaries cannot dissolve mystery entirely. Picture yourself pressing gently against this edge. The solar wind behind you has slowed to a crawl. The interstellar medium ahead resists with its weight. You float in balance, poised between two oceans. The heliosphere cradles you still, but you can see the darker waves of the galaxy beckoning. This is not a hostile place, not an imagination, but a contemplative one. You sense the fragility of our solar system's shield and the immensity of what lies beyond it. Think back to Earth, to the gold record aboard Voyager, engraved with whale songs, greetings in dozens of languages, diagrams of hydrogen atoms, and music from Bach to Chuck Berry. That record is now drifting through interstellar space, a time capsule meant for no one in particular, or for whoever might someday find it. In reality, the odds of interception are near zero, but the gesture itself is profound, a human hello carried on the edge of the sun's breath. The heliopause, then, is more than a boundary, it is a threshold of imagination. On one side lies the known, the solar system, mapped and measured. On the other side, the galaxy vast, uncertain, whispering with mysteries. Voyager's crossing reminds you that thresholds are not barriers but invitations. They say you can step through, you can wonder, you can dream farther. And so you linger here, suspended where the winds meet, listening to the mingling songs of sun and galaxy. The edge does not repel you, it welcomes you. You have drifted beyond the solar system's breath, and yet you are safe, held by the soft current of story, carried onward into the deeper dark. From the threshold of the heliopause, you lean forward and step gently into the dark that belongs to the galaxy itself. Here the protective bubble of the sun thins to nothing, and what greets you are not calm winds but storms of invisible particles. They come from every direction, faster than thought, faster than any spacecraft humanity has ever built. You are in the realm of cosmic rays, the high-energy wanderers of the universe. Cosmic rays are mostly protons, born in violent places, the shockwaves of exploding stars, the spinning remnants of pulsars, perhaps even the turbulent outskirts of black holes. They cross vast gulfs of space, each carrying energy equivalent to a baseball hurled at nearly the speed of light. When they slam into Earth's atmosphere, they shatter into showers of secondary particles, invisible cascades that fall like ghostly rain. You do not see them, but they fall on you every day, passing through your body in the thousands. It is not a horror but a curiosity. Your life has always unfolded under this faint drizzle of the cosmos. A historical fact: in 1912, Victor Hess ascended in a balloon more than 5 kilometers above Earth's surface, carrying instruments to measure radiation. He expected the radiation to drop with altitude, shielded by thinner air. Instead, it increased. From that ascent, the existence of cosmic rays was confirmed, and astronomy was given a new mystery to chase. Humanity discovered not just light from stars, but particles that carried the imprint of distant cataclysms. Above the solar system's north corridor, the cosmic ray storm seems even stronger. Spacecraft and detectors have shown a subtle asymmetry. Slightly more of these high-energy particles arrive from the north than from the south. Scientists puzzle over why. Is the heliosphere tilted, funneling particles unevenly? Do magnetic fields bend them preferentially from one side? Or does the very structure of the galaxy, spiral arms, shock fronts, fountains of plasma, bias their entry? Scientists still argue over the answer, and every new detector adds more pieces without completing the puzzle. And here is a quirky detail: cosmic rays can spark tiny flashes of light inside the human eye. Astronauts aboard Apollo missions reported seeing streaks and bursts even with their eyes closed, as if shooting stars were crossing their vision. The culprit was not imagination, but these particles colliding with retinas in micro-explosions of light. Imagine drifting here, eyes closed, seeing galaxies flicker, not because of stars outside, but because of particles within. It is an intimacy between body and cosmos you rarely think about. At Earth, the atmosphere and magnetic field shield us from most of the damage, breaking the rays apart before they can strike the surface. Yet even here, they leave traces. In polar regions, they generate auroras, curtains of color shimmering as particles slam into atmospheric atoms. They also leave isotopes behind, carbon-14 in tree rings, for example, a clock that helps archaeologists date ancient artifacts. Cosmic rays, then, are not only a hazard, they are also a gift, a tool for measuring time itself. But as you hover in interstellar space, those protections fall away. Here, the cosmic rays pass unbroken. For astronauts dreaming of voyages to Mars or beyond, this is no small challenge. The flux of radiation could damage DNA, overwhelm shields, and slowly, invisibly, erode life. That is why the cosmic ray environment above and below the solar system is not just an academic curiosity. It is a practical question for survival. How thick must the walls of a spacecraft be? What material blocks best? Some suggest water, some plastics, some even propose burying habitats in regolith or ice. Still, none of these solutions are perfect, and the debates go further. The Alpha Magnetic Spectrometer, mounted on the International Space Station in 2011, began detecting something peculiar: an excess of positrons, the antimatter twin of electrons, in the cosmic ray mix. Where do they come from? Pulsars spinning like lighthouses, flinging out antimatter pairs, or dark matter itself, colliding and annihilating in the void? Scientists still argue, fiercely, because the implications touch on the deepest mysteries of physics. Are cosmic rays whispering the existence of the unseen matter that outweighs all stars? You drift here, between these arguments, listening to the hiss of particles. If you could slow them down, you would see them threading along tangled magnetic lines, some bending, some colliding, some vanishing in sudden sparks. They paint no clear picture, only a storm. Yet in their storm lies information. Each carries a story of where it was born, how far it traveled, what forces bent it along the way. Think again of history. In the Cold War years, physicists built giant detectors deep underground, shielded by rock, to study cosmic rays without interference. Some detectors recorded not only cosmic rays, but also neutrinos, those ghost particles born in nuclear reactions and star cores. The same methods that confirmed stellar processes also traced the quiet rain of particles from beyond. Cosmic rays, in this way, became a bridge between astrophysics, geology, and even human history. Now for a fringe tidbit. A few researchers have proposed that bursts of cosmic rays, triggered by nearby supernova, may have subtly influenced Earth's evolution. Some link spikes in isotopes to mass extinctions or climate shifts, suggesting that the heavens may have nudged life's path more directly than we imagine. It remains controversial, but the idea is haunting. Perhaps the death of a star once tilted the scales for life on Earth, setting the stage for us to exist at all. Hover in this thought for a while. Above you, the corridor of polar wind fades into the interstellar medium. Around you, cosmic rays swarm invisibly, countless and relentless. You do not feel them, but you sense their presence, like whispers brushing past. They remind you that space is not empty, that even the void is filled with a rain of energy. For every star you see, there are countless particles you never see, carrying just as much of the galaxy's story. Your breath slows as you take this in. You are safe, watching, imagining. The rays pass through, harmless in this dreamscape, their storm softened into a lull. And in that lull, you realize that the journey above and below is not just about light and structure, but about the hidden forces, the unseen winds and rains, that sculpt the lives of planets and the fates of travelers. You drift onward, your body weightless in imagination, and the hiss of cosmic rays fades into a softer backdrop. Now ahead of you, a structure begins to emerge, not a neat bubble like the heliosphere, not a smooth haze like the interstellar cloud, but something vast and strangely shaped. It curves upward from the galactic plane like a colossal arch, stretching across the northern sky. It glows faintly in radio waves, in X-rays, in subtle hues no human eye alone could detect. This is the North Galactic Spur, one of the most enigmatic features rising above the solar system. Imagine a wall of light and gas, tens of thousands of light-years tall, an arc that seems to trace a circle, though the circle is broken, incomplete. To early radio astronomers in the mid-20th century, the spur looked like an artifact, perhaps a misreading of data, until repeated surveys revealed its persistence. It arcs from the plane of the Milky Way, sweeping toward the north, visible across multiple wavelengths. It is too large to ignore and too strange to explain easily. A historical fact anchors its discovery in the 1960s. Radio maps of the galaxy began to show this feature clearly. As detectors improved, X-ray telescopes joined in, confirming that the spur was not a trick of dust, but a real structure, glowing with high-energy emission. Since then, it has been one of the most studied and most debated structures in galactic astronomy. What is it? That question has never been settled. Some astronomers argue it is a superball, an enormous cavity carved out by multiple supernovae in our local spiral arm. Imagine stars dying in clusters, their shockwaves overlapping, blowing out a giant hollow. The spur would then be the illuminated wall of that hollow, visible from our inside vantage point. Others disagree. They see the spur's scale as too vast, too high above the plane, suggesting instead that it is linked to activity at the galactic center, perhaps a relic of ancient outbursts from the Milky Way's black hole. Scientists still argue, fiercely, each dataset strengthening one case and weakening another. Now for a quirk that delights the poetic mind. If you could see the spur with naked eyes, it would span much of the night sky, a sweeping arc rivaling the Milky Way itself. Instead, it is invisible to ordinary sight, revealed only through instruments. So above your head, each night, hangs a giant luminous arc, a structure thousands of light-years wide, and you never notice. It is the hidden architecture of the galaxy, as present as the stars but cloaked in wavelengths our eyes cannot catch. Picture yourself floating closer. You drift toward the spur's arc, its gases glowing faintly in ultraviolet and X-rays. You feel its texture, not as solid walls but as thin curtains, stretched across space. They shimmer, ripple, bend. In some places the curtains grow thin, letting background galaxies shine through. In others, they thicken, dense with energetic plasma. You pass through and sense the echoes of long-dead stars in the heat of the gas. Debates flare here too. Some astronomers point to its alignment with the so-called loop-eye structure, a giant radio loop that might represent a local bubble around our solar system. Others insist the spur's scale is far larger, demanding an origin tied to galactic-scale explosions. Are we looking at something nearby, a wall of a cavity only hundreds of light-years across? Or are we seeing something vast, tens of thousands of light-years away, a monument to ancient violence at the galactic core? The paradox is unsettling, something so large, so obvious in data, and yet we do not know if it is near or far. You hover within this uncertainty, soothed by the idea that mystery endures even in the age of satellites and surveys. The spur glows above you like a great aurora of the galaxy itself. Its light is not steady but mottled, as if flickering with memory. You drift in its arch, and realize that space is not empty but layered, textured, sculpted by forces you cannot see directly. Think of a historical parallel. In the 19th century, explorers of Earth encountered features they could map but not explain. Vast deserts whose origins and climate were unknown, giant canyons whose slow erosion was unimagined. The spur is like that, a landscape in the sky, mapped with precision yet still begging explanation. Astronomy is still, in some ways, an exploration, a cartography of the unseen. And for a fringe tidbit, some theorists have wondered if the spur could be tied to magnetic phenomena on a grand scale, ribbons of field lines shaped by interactions between the galaxy and intergalactic medium. If true, the spur might not be a thing at all, but an illusion created by our perspective on twisted magnetic fields. It would mean the arc above you is not matter glowing, but geometry bending, a mirage conjured by physics. The idea remains controversial but tantalizing. As you float here, consider what it means that the spur is most visible in the north. If you could fall instead toward the southern pole, you would not see such a structure. The asymmetry itself is curious. Why does the north glow with these arcs while the south remains quieter? Does it mean violence favored one side of the galaxy, or simply that our view is skewed? Scientists still argue, their simulations filled with competing answers. But for you, drifting in imagination, the debates are secondary to the vision. You hover above the solar system, staring into a sweeping arc of light, a structure too vast for eyes but too near to ignore. It reminds you of ancient arches of stone built by human hands, monuments left by forgotten builders. The spur feels like that, a monument carved not by intention, but by explosions, by physics, by time. You linger in its arch, soothed by its scale, comforted by its mystery. And when you turn back, you notice the solar system again, small and dim below. The spur towers above it, a reminder that even home itself floats within larger architectures, structures we cannot yet fully explain. You drift between them, weightless, carried on curiosity alone, as the story carries you deeper. From the glowing arch of the North Galactic Spur, your gaze drifts higher still, and there, towering like twin plumes of smoke rising from a hidden fire, are the Fermi Bubbles. They swell above and below the galactic plane, immense and silent, stretching 25,000 light-years into space. Imagine lifting your eyes in a nighttime meadow and seeing two pale lanterns glowing at the horizon. Except here the lanterns are not on Earth, not even near Earth. They are stitched into the very fabric of the Milky Way itself. The Fermi Bubbles were not always known. For centuries the sky appeared placid, sprinkled with stars and crossed by the faint mist of the Milky Way. Only in 2010, with NASA's Fermi Gamma Ray Space Telescope, did these vast structures reveal themselves. The telescope mapped the galaxy in gamma rays, the highest energy light, and there, flanking the galactic center like balloons tied to an invisible string, were the bubbles. To discover them was like peeling wallpaper from a wall and finding a hidden mural, something immense and startling that had been there all along. A historical fact grounds this vision. The discovery was announced by Douglas Finkbeiner and his team at the Harvard-Smithsonian Center for Astrophysics, who noticed the sharp-edged lobes in Fermi's data. Their symmetry was striking, one bubble above, one below, mirroring each other across the galactic disk. Astronomers knew instantly this was no small feature. It had to be powered by something extraordinary. What caused them? That question is still unsettled. Some believe they were born from eruptions of the Milky Way's central black hole, Sagittarius A*, a monster 4 million times the mass of the Sun. Perhaps millions of years ago it flared, feeding on matter, spitting out twin jets of energy that inflated the bubbles. Others argue they are the result of starburst activity, waves of supernovae exploding in the galactic center, piling shockwaves upon shockwaves, until the energy erupted outward. Scientists still argue which story is true, and the debate itself shapes new observations. Now for a quirky detail, the bubbles are not just visible in gamma rays, they also glow faintly in X-rays, in microwaves, and even in polarized light. They are multi-wavelength lanterns, like paintings layered with invisible pigments. This makes them rich puzzles for astronomers, because each wavelength tells a different story. Gamma rays tracing high-energy particles, X-rays tracing hot gas, microwaves tracing magnetic fields. It is as though the bubbles are speaking in many voices at once, and we are still learning to translate. Float closer now in imagination. Their edges are sharp, almost startlingly so, as if drawn with a cosmic ruler. Inside, the gas glows with energies equivalent to billions of exploding stars, yet the bubbles remain silent, suspended like twin glass domes above and below the galactic center. Their size dwarfs the solar system, dwarfs the spur, even dwarfs much of the Milky Way's disk. You drift along their surface, feeling their immensity, not as a crushing weight, but as a calming vastness, the way the sea calms you with its scale. Scientists debate the bubbles' age. Some models say they formed just a few million years ago, a blink in galactic time. Others suggest they might be tens of millions of years old, relics of ancient violence. The age matters, because it ties to the galaxy's story. Was Sagittarius A** recently active, flaring like the black holes we see in other galaxies, or has our Milky Way been quiet for far longer? Each answer reshapes how we imagine our home galaxy's personality, placid or volatile, slumbering or restless. A historical comparison is tempting here. In the 17th century, when comets streaked across the sky, scholars argued fiercely whether they were atmospheric or celestial. The bubbles evoke the same feeling, immense, obvious once revealed, and yet open to wildly different interpretations. Just as comets once redefined our sense of the heavens, the bubbles now redefine our sense of the galaxy's inner life. For a fringe tidbit, some physicists have speculated that dark matter might play a role in the bubbles' glow. Certain dark matter candidates could annihilate each other, producing gamma rays. If so, the Fermi bubbles might not only be records of astrophysical violence, but also faint lanterns revealing the properties of the invisible matter that outweighs all the stars combined. The idea is controversial, but alluring. Imagine that these towering lobes are both relics of black holes and laboratories of the unseen. You hover now above one of the bubbles, gazing downward at the galaxy, spread like a silver ribbon below. The Milky Way is quiet to your eyes, but within its heart something once stirred violently enough to leave scars taller than the galaxy itself. You sense time differently here, millions of years compressed into a single lingering image, like smoke still hanging long after the fire has gone. And yet, for all their drama, the bubbles soothe you. Their symmetry is gentle, their outlines balanced. They stand like twin guardians above and below, bracketing the galaxy, as if holding it steady. You drift along their edges, and in their vastness you feel no fear, only calm. They remind you that violence too leaves beauty, that explosions fade into symmetry, that chaos sometimes shapes order. Look back down toward the solar system. It is a dot, a mote of dust lost against the backdrop of these towers. Yet that dot contains Earth, oceans, forests, your bed, your resting body. The bubbles stretch above and below it, indifferent yet embracing, monumental yet serene. They are reminders of scale, and scale is always humbling. Scientists still argue whether new bubbles may be forming even now. Data from newer telescopes, like Rosetta, have revealed even more arcs and shells, hinting that the galaxy may be layered with outflows upon outflows. If true, then the Milky Way is not static but breathing, its heart pulsing across millions of years. The Fermi bubbles, then, are not monuments, but moments in an ongoing rhythm. For you, drifting here, the rhythm is soothing. You feel the pulse, slow and steady, like a heartbeat stretched across eons. You let it lull you, a reminder that even cosmic violence softens in time, leaving behind only faint light to cradle the imagination. From the towering lobes of the Fermi bubbles you drift outward, widening your gaze until the Milky Way itself is no longer a single spiral but part of a far greater weave. The galaxy shrinks beneath you, no longer the stage but an actor within a vast ensemble. You are about to step into the grand address of the cosmos, a system of systems, a clustering of clusters, and at its heart lies a discovery from only a decade ago, our true cosmic neighborhood, the Laniakea supercluster. The name means immense heaven in Hawaiian, and the description is no exaggeration. Laniakea is a basin of attraction, a web of more than 100,000 galaxies spanning 500 million light-years across. Our Milky Way swims in one filament of this web, flowing slowly toward the center like a leaf carried by a river. It was in 2014 that astronomers finally mapped this flow with enough precision to declare the Milky Way is not adrift alone, but part of this colossal, coherent structure. Picture it. Galaxies are not static, but drifting, tugged by gravity. Each galaxy's motion is a clue, and when you track thousands of them, you see rivers, streams, currents. Laniakea is defined not by walls of matter, but by these flows. Every galaxy within it moves toward a central gravitational valley, a region called the Great Attractor, itself part of an even larger node of mass. From above and below, Laniakea looks like a cluster of streams converging, rivers feeding into a cosmic basin. A historical fact: before Laniakea, astronomers spoke of the Virgo supercluster, which was thought to contain the Milky Way and nearby groups. But that name was based on proximity, not dynamics. In the early 1980s, scientists like Brent Tully began using peculiar velocity data, the small deviations of galaxies from pure cosmic expansion, to hint at larger patterns. Laniakea was the culmination of decades of this work, finally placing us in a structure vast enough to feel both real and humbling. Now for a quirky detail. The Laniakea supercluster has no true edge. Unlike a country on a map, there is no line where it ends. Instead, its boundaries are defined by flows. If a galaxy drifts toward the Great Attractor, it belongs. If it drifts another way, toward the Shapley concentration, for example, it belongs to another basin. Imagine dividing oceans not by coastlines but by currents, and you have the method here. The galaxy you live in is not pinned to coordinates, but to motion. Drift closer in thought. You see filaments of galaxies, long chains glowing faintly, threading space like strands of spider silk. Between them yawn voids, immense and empty. The Milky Way hangs within one strand, not at the center but on the outskirts, a minor tributary, feeding a cosmic river. Through Sculptor's clean window, astronomers first glimpsed parts of this web. Now with surveys like 2 mass and cosmic flows, the full weave emerges. From above and below, it resembles a lacework, intricate and delicate, yet stretching across unimaginable distances. Debates, of course, stir here too. Scientists still argue whether the Great Attractor is the true heart of our basin, or merely a waypoint, a step on the way to an even larger structure, the Shapley supercluster. Shapley lies farther along the same general direction, brighter and denser, perhaps the real hub. If so, then even Laniakea is only a part of something grander still. The argument reflects the difficulty of defining structures in an expanding universe. Where does one basin end and another begin, if flows stretch without clear boundary? Now pause for a moment of sensory imagining. As you hover above Laniakea, you hear not silence but a faint rushing, like the hush of rivers converging. Each galaxy is a droplet, each filament a stream. The currents converge toward the basin, a soft roar of gravity guiding them. You breathe with it, calm and steady, as if your own pulse has synchronized to the universe's. Here's a fringe tidbit to ponder. Some researchers have speculated that our path through Laniakea may one day affect cosmic microwave background measurements, the faint radiation left from the Big Bang. Because our galaxy moves relative to that background, we already see a dipole pattern, a hot spot in the direction we move, a cool spot behind. As flows carry us, that pattern may shift, subtly altering the fingerprints of the cosmos we record. In this sense, even the background of creation itself bends to the path of our supercluster journey. Think back to earthly parallels. In ancient times, cities were often defined not by walls but by rivers. The Nile, the Ganges, the Tigris, all defined civilizations by the flows they carried. Laniakea is no different. It defines our cosmic civilization, not by boundaries but by currents. You are a passenger in this river, carried unknowingly yet inexorably toward the Great Attractor. You hover now, looking downward. The Milky Way is a tiny spark, the Fermi Bubbles faint scars, the spurs a mere arc. All of them are swallowed in the flow of galaxies, a stream among thousands. It is humbling, but also soothing. To know that you are carried is to know you do not drift alone. Every galaxy here shares the same journey, drawn by the same gravity, flowing in the same grand direction. Scientists still argue whether we will ever map the entire web fully, since dust from the Milky Way hides much of the southern sky, creating what they call the zone of avoidance. Perhaps future instruments, with infrared eyes sharper than any today, will pierce even that fog. For now, the picture is incomplete, but even incomplete, it is astonishing. Rest here in this thought. The solar system has an address, not only in its spiral arm, not only in its galaxy, but in its supercluster, Laniakea. Above and below you see the streams converging, rivers of galaxies flowing through time. It is a quiet revelation. You are not lost. You have a home, nested within structures larger than any city, larger than any nation, larger even than the Milky Way itself. And as you let that thought settle, you feel your breath slow, your eyelids heavy. The immense heaven surrounds you, not hostile, but calm, not empty, but filled with gentle motion. You are carried, always, and in being carried you are safe. From your perch within the immense heaven of Laniakea, you sense that motion is the real language of the universe. Galaxies are not stationary jewels, they are drifting, streaming, forever pulled by invisible currents. And this motion, when traced carefully, reveals our story within the larger cosmos. To understand what lies above and below the solar system, you must now follow those motions, the peculiar velocities that pull us through space, all measured against the faint, eternal glow of the cosmic microwave background. Imagine first the backdrop, the afterglow of the Big Bang, stretched into microwaves by nearly 14 billion years of expansion. It is everywhere, uniform to 1 part in 100,000. Yet when astronomers map it, they see a subtle dipole, a warm side and a cool side. This pattern is not a fingerprint of the early universe, but a reflection of our motion through it. We, along with the entire Milky Way, are moving at about 370 kilometers per second toward a point in the constellation Leo. It is as though the background sky itself were a river, and we feel the headwind of our own drift. A historical fact cements this knowledge. In 1965, Arno Penzias and Robert Wilson stumbled upon the cosmic microwave background while testing a radio antenna in New Jersey. They thought the hiss might be pigeon droppings inside the horn. When they cleaned it and still heard the signal, they realized they had found something fundamental, the remnant glow of creation. Later in the 1990s, the COBE satellite refined the view, confirming the dipole pattern, the clear sign of motion. This was the first precise measurement of our galaxy's peculiar velocity. Now for a quirky note. Our movement is so fast that if you could see the sky in microwave vision, the universe would appear slightly bluer in front of you and slightly redder behind, not unlike the Doppler shift of a passing siren. You live inside a cosmic Doppler effect, wrapped in a subtle color shift invisible to human eyes, but woven into every observation astronomers make, drift upward in imagination. You look down on the Milky Way, not as a disk, but as a vessel carried in a current. Around you, other galaxies stream in the same general direction, toward the gravitational well of the Great Attractor. It is not a place you can see easily, hidden by the dust of the zone of avoidance, but its pull is unmistakable. Entire clusters lean toward it, their velocities betraying the hidden mass. Above the plane, the flows appear like strands of water on glass, each line bending toward a hidden drain. Scientists still argue over what exactly composes the Great Attractor. Is it a concentration of dark matter, invisible but massive? Is it part of the larger Shapley supercluster farther beyond, whose gravity may dominate? Or is it a combination of both, a cascade of attractions, each pulling galaxies like Russian dolls nested inside one another? The debate has persisted for decades, with each new survey revealing both answers and deeper puzzles. As you hover here, you begin to feel the texture of motion itself. Picture thousands of galaxies rushing, their speeds overlapping, some faster, some slower. The collective sound, if translated to your senses, would be like the rush of waves on a shore, a constant shushing that lulls you. Each wave is a galaxy, each shush a million suns carried forward. You close your eyes and let the rhythm soothe you, the ocean of motion rocking you gently. Here is a fringe tidbit. Some astrophysicists have speculated that our passage through these flows could subtly influence the solar system itself. Not directly, not violently, but through long-term modulations of cosmic ray flux or interstellar cloud density. It is an audacious idea that climate on Earth, or even the rhythm of evolution, might carry faint signatures of our galaxy's movement through space. It remains speculative, but it gives you pause. Perhaps history on Earth has always been tied to the great currents above and below. Think back again to the instruments. COBE was followed by WMAP and later by Planck, satellites that mapped the microwave background with ever finer detail. Each revealed the dipole, and each confirmed our motion. Planck in 2013 refined our velocity to that 370 kilometers per second, a value now considered one of the surest truths in cosmology. Through these instruments, humanity has measured not only the age of the universe, but its own path within it. Imagine you are not merely drifting, you are precisely timed, your motion measured against the very afterglow of the Big Bang. Debates still simmer. Some scientists argue whether the dipole is purely due to our motion, or whether deeper, primordial asymmetries exist in the cosmic microwave background itself. Could there be a preferred direction baked into the universe's earliest moments? If so, our movement would not only reveal our place but hint at hidden physics beyond current theory. For now, the safer explanation: our velocity holds sway, but the whispers of anomaly remain. You linger in that thought. Above you, the cosmic microwave background is not just a globe but a canvas against which all motion is drawn. Below you, the Milky Way spins slowly, caught in its arm of Laniakea. Together they paint a picture of belonging. You are not adrift in chaos. You are part of a stream, your direction measurable, your journey shared with galaxies beyond counting. And this knowledge, though vast, is strangely calming. To know where you are moving is to feel less lost. You are not still, but you are guided. The great attractor pulls, the flows converge, and you drift within them like a leaf in a cosmic river. The sound of it is steady, like breath itself. You inhale, galaxies rush. You exhale, galaxies drift. The rhythm is endless, soothing, eternal. Your body softens in the thought. Above and below the solar system lies not only structure but motion, the quiet certainty that we are carried forward. It is not frightening, it is peaceful. You float, rocked by currents invisible, yet absolute, and the immensity of it all begins to feel like a lullaby. You drift now, leaving behind the steady rush of cosmic flows, and tilt your gaze southward once more. For a while, the universe seems smooth, its background calm, its structure orderly, but then, like a ripple across a pond, an anomaly appears. It is faint, subtle, but undeniable. A cold blotch, a patch of sky cooler than its neighbors, large enough to unsettle the neatness of cosmic symmetry. This is the infamous cold spot, one of the most puzzling features discovered in the cosmic microwave background. Imagine the afterglow of the Big Bang spread across the heavens like a woven quilt. For the most part, the quilt is uniform, with tiny temperature variations sprinkled evenly, but in the southern sky, near the constellation Eridanus, one patch stands out, a region about 70 microgavans cooler than expected, spanning an area larger than the Moon. To most people, the difference would be meaningless. To cosmologists, it was shocking, because the background should be smooth, its ripples random but statistically predictable. The cold spot broke the rules. A historical fact fixes this moment. In 2004, the WMAP satellite published full-sky maps of the microwave background, and the cold spot leapt out. Later, the Planck satellite in 2013 confirmed it was real, not an artifact of instruments or noise. From then on, it became a focal point of debates and speculation, and those debates rage still. Some argue the cold spot might be the imprint of a massive supervoid along our line of sight, a region of space unusually empty of galaxies. Light traveling through such a void would lose energy, cooling slightly, creating the observed dip. Others counter that the voids discovered in surveys are not large or empty enough to account for the full anomaly. Scientists still argue whether the cold spot is a statistical fluke, a sign of cosmic structure, or a clue to new physics. Now for a quirky note. When astronomers first announced the cold spot, newspapers picked it up with sensational headlines, some claiming it was evidence of another universe brushing against ours. The idea came from speculative theories of cosmic inflation, where our universe might be one bubble among many. A collision between bubbles, some theorists mused, could leave behind exactly such a cold bruise. The speculation remains fringe, but it caught imaginations worldwide, proof that even small temperature dips can stir dreams of infinite worlds. Float closer in imagination. You gaze at the patch of sky, its subtle coolness invisible to your eyes, but glowing on microwave maps. It feels eerie, as though the universe itself wears a scar, a reminder that not all is smooth. The rest of the cosmic background hums around you, its warmth steady, but this patch lingers, quiet and colder, as if holding a secret. Scientists still argue about its implications. If it is a fluke, then our universe remains consistent with the standard model of cosmology, neat and symmetrical. If it is real, caused by a void or some other process, then the universe may be stranger, less tidy, shaped by features we do not yet understand. And if, by some remote chance, it is evidence of a multiverse collision, then it changes everything, making our cosmos one among countless others. The arguments oscillate, the evidence weighs, but no conclusion has silenced the debate. Pause now and imagine the soundscape. Where the rest of the microwave background hums like a steady drone, the cold spot would sound like a low drop, a softer tone woven into the chord. It does not interrupt, but it unsettles, like a missing note in a familiar song. You linger on it, letting its difference remind you that perfection is not the universe's goal. Even the cosmos has quirks, asymmetries, oddities that refuse to fit into models. Think back to history again. In the early 20th century, when Edwin Hubble revealed that galaxies were rushing outward in expansion, many doubted him, clinging to steady-state models. The cold spot echoes that sense of unease. Sometimes anomalies force paradigm shifts, sometimes they fade into noise. The suspense is part of science itself. Here is a fringe tidbit to carry with you. Some cosmologists propose that the cold spot might represent a texture, a relic of topological defects formed in the early universe when fundamental forces separated. These hypothetical textures would be scars in space-time itself, left over from cosmic phase transitions. If true, then the cold spot is not a void or a fluke, but a fossil of creation. No evidence yet confirms this, but the notion whispers of physics deeper than the known. Hover above the southern sky now. The cold spot is beneath you, not glaring but muted, a faint dimming on the great canvas of the microwave background. Around it, galaxies cluster, voids yawn, filaments stretch. It does not dominate the sky, but unsettles it, like a question left unanswered in the middle of a story. You breathe, slow and calm, knowing that unanswered questions are not threats but invitations. Above and below the solar system lie not only grand structures like bubbles and spurs, but also mysteries like this, quiet anomalies that hint at truths beyond reach. You let that thought cradle you. The cold spot is not frightening. It is soothing in its reminder that the universe is not entirely mapped, not fully explained. There will always be more to wonder about, more to dream of, more to drift toward in imagination. And so you linger, gazing into the cooler patch, feeling its quiet difference. Your eyelids grow heavy. The anomaly becomes less a puzzle and more a lull, a gentle irregularity that rocks you softly, like a boat nudged by a wave. You realize the cosmos does not need to be symmetrical to be beautiful. Its very imperfections make it human to behold, calming to contemplate, a mystery worthy of sleep. Beyond the faint chill of the cold spot, your imagination drifts further, settling into the unseen. The galaxies around you sparkle, filaments glow, but you begin to sense that most of what surrounds you is invisible. Matter you cannot see outweighs the matter you can. Above and below the solar system, through every corridor of the galaxy, there is a hidden scaffold shaping what you witness. This is the domain of dark matter, the unseen mass that holds galaxies together and perhaps forms vast structures we cannot yet detect directly. Picture yourself floating in the galactic halo. Stars thin, gas clouds vanish, but the gravitational tug remains strong. It is as though you are resting on glass too clear to see, transparent yet firm. Astronomers have known for decades that the Milky Way contains more mass than its stars, gas, and dust account for. The proof lies in the way stars orbit. If the galaxy were made only of visible matter, the outer stars would move sluggishly, slowed by weak gravity. Instead, they race as though something massive were pulling them, something invisible. A historical fact grounds this story in the 1970s. Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies, including the Andromeda Galaxy. They found that instead of slowing at the edges, stars continued orbiting at high speeds, betraying the presence of hidden mass. This was the quiet revolution that confirmed dark matter's importance. Without Rubin's patient observations, we might still dismiss the galaxy's scaffolding as a mathematical trick. Now for a quirky detail. Dark matter does not clump like stars or gas. It passes through itself, through us, through Earth, largely unnoticed. Every second, trillions of dark matter particles may stream through your body without leaving a trace. It is a strange intimacy, always present, never felt. You are more ghosted by it than touched by the starlight you see. Imagine lying in bed, the night silent, while invisible tides of matter drift through the room, through the walls, through your bones, unnoticed yet fundamental. Debates surround this hidden world. Scientists still argue what dark matter actually is. Some favor WIMPs, weakly interacting massive particles that might be detectable with sensitive underground detectors. Others argue for axions, feather-like particles that might reveal themselves in magnetic fields. Still others suggest sterile neutrinos, or even modifications to gravity itself. Despite decades of effort, no experiment has directly caught a dark matter particle in the act. The mystery remains one of physics' deepest, above and below the solar system. Theorists imagine that dark matter might pool, not evenly, but in sheets or streams. The galaxy's disk could be threaded with invisible layers, like pages of a book. Some simulations suggest that passing through these dark streams could alter the flux of cosmic rays or subtly change the orbits of stars. If so, then what lies above and below is not only gas or stars, but ghostly rivers of unseen matter flowing endlessly. Float now through one of those imagined streams. You see nothing, feel nothing, and yet the galaxies around you cling to it like dew on a spider web. The stream curves, loops, threads its way across the halo, binding clusters together. It is structure without form, presence without light. You drift through it easily, unharmed, and sense that the universe is larger than visibility admits. Here is a fringe tidbit to carry into the dark. Some researchers have speculated that planets, even Earth itself, might pass through clumps of dark matter over millions of years. Such encounters could slightly heat planetary cores, subtly influence geology, or even alter evolution by shifting cosmic ray flux. The evidence for this is tenuous, but it hints at a startling idea that Earth's history may have been nudged not only by asteroids and comets, but by invisible rivers of matter gliding through the galaxy. Think of the historical resonance. In ancient times, sailors navigated oceans guided by stars they could see, yet beneath them were currents they could not. Dark matter is the unseen current of the galaxy, steering stars, galaxies, and perhaps even life. To live within the Milky Way is to ride an ocean we cannot measure fully. Scientists still argue whether dark matter is evenly spread, or if it forms a disk aligned with the galaxy's plane. If such a disk exists, then above and below the solar system might hold denser regions, an invisible sandwich around the stars. The debate remains unresolved, with data from missions like Gaia helping to test the idea. If true, then the solar system is not merely suspended in starlight, but nestled between layers of unseen substance. Pause here in imagination. You are surrounded by silence, by absence, by weight you cannot feel. The dark matter halo envelops you, calm and endless. It does not glow, it does not speak, yet it holds galaxies in its grip, preventing them from tearing apart. Its quiet strength is soothing, like a hand holding the universe steady while you drift. And so, above and below the solar system, you realize, lie not only visible wonders, but invisible guardians. Dark matter does not shimmer like stars or roar like cosmic rays, but it sustains the stage on which all else unfolds. You let the thought cradle you that the most important things in the universe may be the ones you cannot see, the ones that pass through you in silence. From the invisible scaffolding of dark matter, you drift into stranger territory still, into the realm of particles that may or may not exist, into the speculative frontier where science leans on hope as much as measurement. Here, in the quiet above and below the solar system, some dream of elusive quarry, magnetic monopoles, single poles of magnetism wandering alone through space. Imagine holding a bar magnet in your hand. Break it in half, and each half grows its own north and south. Break it again, and still every fragment has two poles. No one has ever isolated a north without a south, or a south without a north. And yet, theory suggests they should exist. If they do, the cosmos might be threaded with them, relics from the earliest fractions of a second after the Big Bang. A historical fact grounds this possibility. In 1931, Paul Dirac, one of the great pioneers of quantum theory, showed that if even a single magnetic monopole existed anywhere in the universe, it would explain why electric charge is quantized, why every electron carries exactly the same charge. It was an elegant piece of reasoning, and ever since, physicists have searched, now for a quirky detail. Because monopoles are hypothetical, they inspire unusual detection methods. In the 1980s, researchers built detectors filled with liquid helium, hoping a monopole would pass through and flip atomic nuclei like compass needles. Others set out cosmic ray detectors, dreaming a monopole might trigger them. Once in 1982, an experiment in Utah reported a candidate event, a strange burst of energy in a superconducting loop. The press briefly celebrated the discovery of the monopole, yet follow-up attempts never reproduced it. To this day, that lone blip is catalogued as mysterious but unconfirmed, and so the debates endure. Scientists still argue whether monopoles should be abundant, a natural relic of early cosmic symmetry breaking, or vanishingly rare, swept away by inflation in the first microseconds of time. Some models insist they must exist, hidden in the depths of space. Others quietly suggest that perhaps they never did. The absence of evidence after decades of searching keeps the field restless but alive. Hover now in imagination above the southern sky, where magnetic fields are calmer, less tangled by star-forming regions. Some theorists argue that if monopoles drift anywhere, they might be easiest to find in such quiet zones. You float through that silence, picturing solitary particles, invisible, moving at cosmic speeds, each one carrying a magnetic charge that no compass could resist. They do not glow, they do not leave trails like comets, but their presence would warp fields around them in subtle, unmistakable ways. Think of history's persistence. For centuries, alchemists searched for philosopher's stones that might transform matter. Today, physicists chase monopoles with equal fervor, not for gold but for understanding. Both quests are driven by the same spark, the suspicion that nature hides treasures just out of reach. Here is a fringe tidbit to stir your thoughts. Some researchers speculate that monopoles, if they exist, might bind to cosmic strings, hypothetical filaments of energy stretched across the universe. If so, then above and below the solar system could be littered not just with lone monopoles but with strings and beads, like necklaces from the dawn of creation. It is an idea born of theory more than data, yet it paints the cosmos with mythic imagery, as if the universe wears jewelry invisible to us. You pause here listening. If monopoles sing, their music is faint. Perhaps it is nothing more than the occasional flip of a magnetic field, a subtle twist in the hum of plasma. You let the quiet seep in, knowing that science often waits decades, even centuries, for whispers to grow into songs, and you find comfort in the uncertainty. The monopole has never been caught, but the search itself is part of the human rhythm, to imagine, to reach, to question. Above and below the solar system, you drift through possibilities as much as through particles, each one a reminder that knowledge is not only about answers, but about the courage to ask. Your breath slows. The invisible world becomes a cradle, filled with might-be's and what-ifs. You let yourself be carried by it, not fearing the unknown but resting in its promise. Perhaps one day a detector will chime, a field will flip, and a lone magnetic pole will reveal itself, or perhaps not. Either way, the dream itself has shaped how we see the universe, and that dream lulls you now into deeper calm. You drift onward, leaving the speculation of monopoles behind, and soon you sense the hum of instruments, the quiet heartbeat of humanity's surveys and telescopes. The cosmos above and below the solar system has been unveiled, not by naked eyes, but by lenses, detectors, and patient mapping. To understand what we know and what we still long to see, you must glide through the history and future of these tools, the surveys that gave us cosmic structure, and the next generation observatories poised to deepen the story. Begin with a memory of early efforts. Astronomers once mapped the heavens with pencil and paper, star by star, catalogue by catalogue. Then came the photographic plates of the 20th century, where galaxies were caught like ghosts on glass. But the great leap arrived with digital surveys. In the late 1990s, the Sloan Digital Sky Survey, SDSS, began scanning the northern sky with a dedicated 2.5-meter telescope in New Mexico. Its vast database revealed millions of galaxies, their redshifts measured, their clustering mapped. For the first time, we saw not just stars and galaxies, but the large-scale structure, the cosmic web, filaments and voids stretching across space. A historical fact grounds this revolution. In 2005, data from SDSS revealed the largest structures ever mapped, walls of galaxies spanning hundreds of millions of light-years. One of them, the Sloan Great Wall, shocked astronomers with its immensity, challenging earlier ideas of how uniform the universe should be. Through SDSS, the north sky became a canvas of filaments, while the south awaited its equal. And so came the 2-micron all-sky survey, 2MASS, peering in infrared to cut through dust, reaching galaxies hidden in the so-called zone of avoidance near the galactic plane. Suddenly, the map filled in, showing flows toward the Great Attractor, tying north and south into a continuous web. Later, cosmic flows surveys measured peculiar velocities, not just positions, tracing the currents of motion that defined Laniakea. These were not mere maps but dynamic charts, revealing the rivers of galaxies flowing above and below us. Now for a quirky note. These surveys produce so much data that astronomers coined playful names for their maps. The zone of avoidance, for example, is not forbidden by physics, only by dust, like a foggy windshield blocking part of a road. Other regions gained nicknames like the local void or the Great Wall, names that sound more like fantasy landscapes than science. It shows how even the most rigorous data can spark imagination when the scales are this vast. You drift among these digital star charts now. They are not paper maps but glowing webs, three-dimensional lattices stretching into your vision. You see the gaps, the rivers, the clusters, the attractors. It is as though you are floating through stained glass, with filaments like leadwork holding galaxies in place. Above and below, the patterns are not random, they are ordered, though not fully understood. Scientists still argue about the completeness of these surveys. Dust and distance obscure much. Are there hidden superclusters in the far southern sky, still cloaked from view? Are we missing structures that could redefine our flows? Future observatories will decide, and the future is dazzling. The European Space Agency's Euclid mission, launched in 2023, is designed to map billions of galaxies across a third of the sky, measuring shapes and redshifts to probe dark energy and dark matter. Its wide-angle vision will sharpen our maps above and below, filling gaps with unprecedented detail. Then comes the Vera C. Rubin Observatory, preparing its legacy survey of space and time, LSST. Over 10 years, it will image the entire southern sky again and again, producing the deepest, widest movie of the cosmos ever made. Every flicker of light, every shift of galaxy, will be catalogued. Imagine watching the universe breathe, frame by frame, across a decade. And on the horizon waits NASA's Nancy Grace Roman Space Telescope, equipped with a wide-field instrument capable of capturing swaths of sky 100 times larger than Hubble ever could, yet with similar sharpness. Roman will probe both the faint arcs of gravitational lensing and the clustering of galaxies, expanding our vision into both depth and breadth. Here is a fringe tidbit. Some astronomers have begun speaking of cosmic cartography, not just as science but as art. They display survey maps in galleries, turning data into glowing murals of filaments and voids. Visitors, unaware they are looking at real positions of galaxies, stand in awe as if before abstract art. The idea blurs the boundary between knowledge and beauty, reminding us that the maps of above and below are as aesthetic as they are scientific. Hover here a moment longer. You imagine drifting into the Rubin Observatory's database, swimming through billions of points of light, each one a galaxy with its own stars and planets. You glide past the arcs of gravitational lensing that Roman will measure, like warped glass bending the light of background galaxies. You float alongside Euclid's catalogues, rivers of redshift data streaming past. The instruments hum around you, not with noise but with numbers, and you realize that this is how humanity explores now, not by sails or oars but by surveys. Scientists still argue how far these surveys can take us. Will they solve the puzzle of dark energy, or merely sharpen its strangeness? Will they reveal new attractors, new anomalies, or confirm the symmetry of the cosmos? Each question lingers, waiting for data, waiting for patience, and in the meantime, you rest in their promise. Above and below the solar system, the cosmos is no longer unknowable. It is mapped, imperfectly but beautifully, by instruments designed with care, built with vision, launched with hope. These maps cradle you now, letting you drift through filaments and flows, comforted by the fact that humans are not blind here. We are cartographers of the infinite, dreamers with data in hand. From the humming promise of telescopes and surveys, you drift deeper into a realm not of instruments, but of imagination. Above and below the solar system, astronomers suspect lie not only filaments and voids, but the subtle warp of space itself. You feel the invisible tension of cosmic fabric stretched, bent, and curved by forces beyond ordinary matter. This is the frontier of dark energy, the most mysterious actor in the universe, the one that accelerates expansion, the one that refuses to reveal its true face. Picture the cosmos as a balloon, dotted with galaxies like painted specks. For much of history, astronomers thought the balloon might expand forever at a slowing pace, or collapse back under gravity. Then came the surprise. The expansion is not slowing, it is speeding up. The balloon stretches faster and faster, as though something unseen is pushing from within. That push is dark energy. A historical fact anchors this revelation. In 1998, two teams of astronomers studying distant supernovae discovered that these exploding stars were dimmer than expected. The only explanation was that the universe's expansion had accelerated over the last several billion years. It was a Nobel Prize-winning shock, rewriting cosmology. What had been a simple contest between expansion and gravity became a deeper puzzle. An invisible pressure permeates the cosmos, accounting for nearly 70% of its energy. Now for a quirky note. One of the earliest names suggested for dark energy was quintessence, echoing ancient philosophy. The Greeks spoke of a fifth element beyond earth, air, fire, and water, a pure ether that filled the heavens. Today's quintessence, if real, would be a field that changes over time, unlike Einstein's simple cosmological constant. In a strange way, modern physics circles back to ancient imagination, weaving myth into equations. You drift above the galactic plane, sensing this pressure. It does not pull like gravity or push like wind. It is subtler, the space between galaxies stretching faster and faster, carrying them apart. Imagine lying on an ocean where the waves beneath you grow taller, not by wind but by some hidden tide swelling from within. You feel it without seeing it, and the calm of its inevitability washes over you. Scientists still argue about the nature of dark energy. Is it truly Einstein's cosmological constant, a fixed property of space itself, or is it something dynamic, evolving, a field that waxes and wanes? Some even wonder whether our understanding of gravity itself must be rewritten. Modified gravity theories propose that what we see as acceleration may be an illusion, a sign that our equations are incomplete. No consensus has emerged. The debates are open, passionate, unresolved. Hovering in imagination, you see the cosmic web stretched taut by this force. Filaments elongate, voids swell, galaxies drift further apart. Over billions of years, the universe becomes more diffuse, more isolated. If dark energy remains constant, then eventually only local groups of galaxies will remain bound. All others will slip away beyond visibility. From Earth in some unimaginably distant future, the sky may be nearly empty. The Milky Way's cluster all that remains. Here is a fringe tidbit. Some theorists have suggested that dark energy could be unstable, that it might one day flip sign, becoming attractive instead of repulsive. In that scenario, the expansion would halt and reverse, collapsing in a big crunch. Others push stranger still, imagining phantom energy that grows stronger with time, tearing apart galaxies, stars, planets, even atoms in a big rip. These ideas are speculative, but they show how dark energy keeps the imagination alive with both creation and destruction. Pause to imagine the soundscape. If dark energy had a sound, it would not be a roar but a low swelling hum ever present, growing slightly louder as the universe expands. a bass note beneath the cosmic symphony, steady, inescapable, shaping the rhythm of everything else. You listen, and it steadies your breathing, long and slow, matching the pulse of expansion itself. Think back to Einstein. In 1917, he inserted the cosmological constant into his equations to keep the universe static, a balance against collapse. When Hubble showed the universe was expanding, Einstein abandoned it, calling it his greatest blunder. Yet decades later, the constant returned, this time as the best explanation for acceleration. History itself seems to mock certainty. What once was discarded returns as essential, and you realize above and below the solar system lies not only matter, not only void, but mystery woven into the fabric of space-time. A pressure no hand can feel, a force no eye can see, yet one that determines the fate of everything. It is humbling, but it is also oddly soothing, to know that the cosmos expands not into chaos, but into a rhythm, guided by laws we glimpse but do not yet master, is to feel held by something larger than yourself. Scientists still argue whether dark energy will remain constant forever or change, whether it will tear the universe apart or simply stretch it thinner and thinner. The arguments do not trouble you, they lull you because they remind you that the universe is not finished. It is alive, dynamic, still telling its story. You exhale slowly. Dark energy is everywhere, above and below, around and within. It does not frighten you. It rocks you gently, like the unseen current of an ocean beneath a boat. You close your eyes, drifting on the calm certainty that while stars burn out, while galaxies move apart, the expansion itself will carry on, and in that inevitability, you find rest. You float now in the slow hum of expansion, letting the echo of dark energy fade into the background. Above and below the solar system, the great structures of the cosmos continue to sway, held not only by gravity and invisible scaffolds, but also by time itself. And it is here that you begin to notice something subtler than energy, stranger than matter, the possibility that the universe's shape may not be what it seems. For centuries, people assumed the cosmos was infinite and flat, stretching outward in every direction without end. Then came general relativity, with its suggestion that space could curve, just as the surface of Earth is finite yet unbounded. You can walk around it forever without finding an edge. So too might space itself curve back on itself, forming a closed shape too vast to imagine. Above and below the solar system, therefore, may not simply mean up and down in an infinite expanse, but different arcs along a cosmic curvature, bending silently around you. A historical fact grounds this realization. In 1917, Willem de Sitter and Albert Einstein introduced the first relativistic models of the universe. Einstein's was static and curved, while de Sitter's expanded. Both admitted possibilities more complex than infinite flatness. Later, observations of the cosmic microwave background by Kobe, Bedouin-Mappé, and Planck refined the story, showing that on large scales the universe appears remarkably flat, but not perfectly so. Measurements remain precise but not absolute, leaving room for curvature at scales beyond current reach. Now for a quirky note. Some cosmologists playfully compare the universe's potential shape to donuts or pretzels. A toroidal cosmos, a giant three-dimensional donut, could in principle allow a traveler to move in one direction long enough and return to their starting point. Imagine setting off above the solar system, journeying straight through endless black, and after billions of years reappearing below it, like a sailor circumnavigating a spherical Earth. It is speculative, yes, but the mathematics allows it. You drift further, imagining yourself tracing such a loop. The stars around you shift, galaxies slide away, yet the trajectory is not endless but curved, a path returning without edge or boundary. In this vision, there is no outside to the universe, only inside, endlessly connected, looping upon itself. Scientists still argue whether space is exactly flat or slightly curved. Current data suggest it is very close to flat, but small deviations are difficult to rule out. Even if the observable cosmos looks flat, the true global shape could still be spherical, hyperbolic, or toroidal. These debates stretch into philosophy. Is what we see all there is, or just a patch of a larger whole? Pause and imagine the soundscape of such curvature. It is not silence but a faint resonance, like the echo of a bell rung long ago, sound waves wrapping around a hollow chamber. Some cosmologists have searched for repeating patterns in the microwave background, echoes that would suggest a closed shape. None have been found yet, but the search continues, the echoes imagined, waiting to be heard. Here is a fringe tidbit to stir you. Certain multi-connected universe models predict that if you looked far enough in the right direction, you might see a duplicate of the Milky Way, light looping around the cosmos and returning from another path. In such a scenario, above and below the solar system could contain ghostly mirrors of our own galaxy, faint repetitions of familiar constellations. The absence of such echoes so far suggests the universe is larger than the part we see, but the idea lingers, teasing like a mirage. Think of the ancient parallel. Sailors once debated whether Earth was flat or curved, whether a ship might fall off its edge or return again by circling. Today, cosmologists ask the same of the universe itself. What lies above and below may depend not only on position, but on geometry, the hidden curvature of space. Hover in that thought. If the universe is flat, then above and below extend forever, infinite layers of galaxies, filaments, and voids, repeating endlessly. If curved, then above and below might one day meet, folding back upon each other. Either way, the solar system is suspended in a structure grander than any globe or map, carried by a fabric whose edges may not exist. Scientists still argue whether quantum gravity, an eventual union of relativity, and quantum mechanics will settle the question. Perhaps new physics will show that space-time is granular, like a lattice, with curvature emerging only on large scales. Perhaps future observations of gravitational waves or cosmic neutrinos will reveal subtle bends invisible to photons. For now, we float in possibility, patient cartographers of geometry itself. And you, drifting above and below, feel no urgency. The debates, the shapes, the possibilities, they are not threats but lullabies. You rest in the knowledge that whether flat or curved, infinite or finite, the universe holds you gently within its fabric. No edge threatens, no drop awaits. You are enfolded, contained, secure. Your breath deepens. The idea of infinite flatness soothes you, endless repetition, no boundary to stumble upon. The idea of curvature soothes you too, a closed embrace, a loop that carries you home. Either path is comforting, each one a cosmic cradle. You close your eyes, letting the geometry fade into rhythm. Above and below the solar system lies not only matter, not only energy, but the possibility of shapes beyond sight, curves beyond imagining. And in that mystery, you find peace. The thought of cosmic curvature lingers in your mind, like the afterring of a struck bell. You let it fade, and in the silence that follows, another layer of the unseen comes into focus. Not matter, not geometry, but time itself. Above and below the solar system, the universe is not only structured in space but in eras, epochs stacked like strata. You are floating not just through distance but through history, gliding across the sediment of cosmic time. Picture it this way: when you gaze into the night sky, you are not looking at stars as they are now, but as they were. Light takes time to travel, and so every star is a message from the past. A nearby star may be a decade-old message. A galaxy may be millions of years old. And the farthest galaxies visible through telescopes whisper from billions of years ago, when the universe itself was young. Above and below, in every direction, you are surrounded by time capsules rather than snapshots, a layered chronicle stretching backward. A historical fact anchors this. In the 1920s, Edwin Hubble measured galaxies' redshifts and distances, realizing that the farther a galaxy lay, the faster it was receding. His discovery meant not only that the universe expands, but that the farther you look, the younger the cosmos you see. Each step outward is a step backward in time. The telescope became a time machine, showing not one moment but a sequence of moments, stacked across billions of years. Now for a quirky detail: the deepest image ever taken, the Hubble Ultra Deep Field, was not a photograph of the present, but a mosaic of the ancient. Hundreds of hours of exposure in one small, apparently empty patch of sky revealed 10,000 galaxies, each one frozen in an age when Earth itself did not yet exist. That small speck of sky, no larger than a grain of sand held at arm's length, became a window to epochs long before the solar system formed. You float in imagination into such a field. The galaxies around you are not uniform. Some are twisted, irregular, their arms clumsy. These are infant galaxies, still merging, still colliding, still shaping themselves. The light you see left them when the first stars were just beginning to burn heavier elements, carbon, oxygen, the very atoms that would one day form your lungs, your breath. Above and below, therefore, are not only different directions in space but different chapters in time, stacked like pages in a book. Scientists still argue how early galaxies formed so quickly after the Big Bang. The James Webb Space Telescope JWST, launched in 2021, has already revealed galaxies brighter and larger than models predicted at only a few 100 million years old. Are these galaxies anomalies, or is our understanding of cosmic dawn incomplete? The debates ripple through astrophysics, forcing new simulations, new theories, new questions. Pause for the soundscape of time. If each galaxy's light were a note, you would hear a descending scale, nearby galaxies humming high, ancient galaxies humming low, their pitch stretched by redshift into deeper tones. Around you the cosmos plays not a single chord but a symphony of ages, each note a different time. You float within it, cradled by music as old as creation itself. Here is a fringe tidbit. Some researchers speculate that time itself may not be uniform, that in certain conditions, near black holes in quantum regimes, it may behave differently, or even emerge from deeper structures rather than being fundamental. If so, then the layers of history you drift through are not carved in stone, but woven from rules we have yet to decipher. Perhaps before and after are local illusions, and what you see as epochs are only shadows of something larger. Think of history again. On Earth, archaeologists dig through layers of soil, finding pottery, bones and fossils that tell the story of civilizations and species. In the sky, astronomers dig through layers of light, uncovering galaxies and quasars that tell the story of cosmic evolution. Above and below the solar system are strata of photons, fossils of starlight, a cosmic archaeology carved not in rock but in radiation. Hover here a moment. You imagine brushing away cosmic dust like an archaeologist's hand, revealing deeper layers of light, older galaxies, fainter whispers. Each one is fragile, ancient, precious. They remind you that your own life is a fleeting surface, a moment resting on billions of years of cosmic history beneath. Scientists still argue whether there is a limit to how far back we can see. The cosmic microwave background, 380,000 years after the Big Bang, is often called the Wall of Sight, the point before which the universe was opaque to photons. But some dream of neutrino observatories or gravitational wave telescopes that might pierce even deeper, glimpsing the universe's first second. To see such an era would be to touch the beginning itself, to hear the first heartbeat of time, and yet you are calm in not knowing. You drift above and below, surrounded by epochs, and let their weight steady you. Time is not a burden here, it is a lullaby, rocking you with its immensity. The galaxies hum, the epochs murmur, and you close your eyes to their song. Above and below the solar system lies not only space but time, not only distance but depth. Every photon you see is a story told across ages, every star a memory that arrives long after its birth. You are adrift in a library written in light, each page infinite, each word a reminder that the cosmos is older, vaster, and more enduring than any fear. You let that thought carry you. The ages above and below are not hostile, they are gentle, steady, patient. They wait for you, as they have waited for billions of years, and in their patience you find rest. From the layers of time, you drift outward once more, not through epochs of light, but through the deeper fabric beneath them. Above and below the solar system, the galaxies and voids, the filaments and flows, the structures of matter are all strung upon a hidden loom. It is a loom made not of photons or particles, but of vibrations in space-time itself, gravitational waves, ripples spreading silently through the cosmos, carrying with them the memory of violent beginnings and ancient collisions. Imagine space-time as a vast ocean. Drop a stone into water, and ripples spread across its surface. Now replace the stone with two black holes spiraling together, their immense masses warping space-time. The collision sends waves radiating outward, stretching and squeezing the fabric of reality. Those ripples, traveling at the speed of light, pass above and below the solar system, even now, faint and constant, whispering the story of events you could never otherwise witness. A historical fact gives this story weight. In 1916, Albert Einstein predicted gravitational waves as a consequence of general relativity. He doubted they would ever be detected, thinking them too weak. But a century later, in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, announced the first direct detection, two black holes merging over 1 billion light-years away. The detectors in Louisiana and Washington registered a fleeting chirp, less than a second long, but it confirmed Einstein's prediction and opened a new era of astronomy. Now for a quirky note. The sound of that first detection was converted into audio for human ears, a rising whoop, often called the chirp. It lasted just fractions of a second, yet it contained the death spiral of two black holes, each about 30 times the mass of the Sun. You live in a universe where space-time itself can sing, and scientists can listen. Above and below the solar system, waves like these pass continually, silent until caught by instruments fine enough to notice them. You drift now through that invisible sea. You do not see galaxies. You feel the faint undulation of space-time, stretching and compressing, stretching and compressing. It is a rhythm too subtle for flesh to detect, but steady, infinite, patient. The solar system, the Milky Way, even Laniakea itself is rocked ever so slightly by these ripples. They pass through without harm, like gentle tides brushing against a boat. Scientists still argue about the sources of these waves. While black hole and neutron star mergers are confirmed emitters, theorists predict a background of gravitational waves from even earlier epochs, perhaps from inflation itself, the rapid expansion in the universe's first instant. Detecting such primordial waves would be like hearing the echo of the universe's birth cry. Instruments like pulsar timing arrays, which use the steady beat of millisecond pulsars as cosmic clocks, now hint at this background. The debates are lively. Is the signal already detected, or are we still listening to noise? Pause and imagine the soundscape of gravitational waves. It is not static or uniform, but a layered choir. Some waves are quick chirps, black holes colliding. Others are slow, deep notes, the long hum of supermassive black holes spiraling over millions of years. Together they form a cosmic symphony, vibrations playing endlessly across space-time. You float within it, and the music steadies your heartbeat. Here is a fringe tidbit. Some physicists suggest that gravitational waves, unlike light, may pass freely through extra dimensions if such dimensions exist. In that case, detecting anomalies in their propagation could reveal hidden aspects of reality beyond our three-dimensional space. Above and below the solar system, therefore, these ripples might not only carry news of collisions, but whispers of deeper geometry. It is speculation, but it reminds you how every ripple might hold a secret larger than its source. Think back to human history again. Mariners once listened for the sea's voice, the crash of waves, the hiss of currents, the groan of winds in sails. Today, astronomers listen for space-time's voice, the whoop of black holes, the hum of the early universe. Different oceans, same instinct to know where we are by the music around us. You hover above the galactic plane, the solar system beneath you like a pearl on a thread. The gravitational waves pass both above and below, bending space-time ever so slightly. They are not frightening. They do not threaten to tear worlds apart. They are whispers, not roars, proof that the universe is alive with motion and memory. Scientists still argue whether the ultimate background of gravitational waves will ever be separated from noise. The Earth itself vibrates, lasers fluctuate, instruments shiver with thermal energy, yet patience and persistence yield progress. Each year, detectors sharpen, new observatories rise, and the song of space-time grows clearer. And you, adrift in imagination, find calm in the thought. Above and below the solar system lies not only light but sound, not only particles but waves, not only matter but memory. The universe hums, and you are part of its resonance. You close your eyes and feel rocked by the rhythm, as though space-time itself has become your cradle. Your breath slows. The ripples pass through, endless, gentle, inevitable. They do not disturb you, they steady you. You are held by a universe that not only shines but sings. The ripples of space-time fade into the background of your awareness, leaving you suspended in a universe that is not silent but layered with whispers. Above and below the solar system, beyond gravitational waves and luminous webs, there exists something subtler still, the faintest particles, the lightest messengers streaming everywhere, almost without end. They are neutrinos, ghost-like travelers that pass through planets, stars, and your very body without pause. If gravitational waves are the universe's music, neutrinos are its breath, flowing steady and unstoppable, unseen but constant. Imagine them nearly massless, faster than imagination, immune to most interactions. Every second, tens of trillions pass through you. They slip through walls, oceans, even the Earth's core, hardly noticing matter at all. They come from the sun, from distant stars, from supernovae, from the Big Bang itself. Above and below the solar system, neutrinos form a silent river, a background sea against which all else plays out. A historical fact grounds their story in 1930. Wolfgang Pauli proposed the neutrino to solve a puzzle in beta decay. Energy and momentum seemed to vanish when certain radioactive particles decayed. Pauli suggested that an invisible particle carried away the missing balance. He apologized in his letter to colleagues, saying he had introduced a particle that cannot be detected. For decades it remained a ghost of theory, until in 1956, Clyde Cowan and Frederick Rines finally confirmed neutrinos experimentally, using a nuclear reactor as a source. Now for a quirky note. Neutrinos come in three flavors: electron, muon, and tar, and they mysteriously oscillate between these identities as they travel. A neutrino born in the heart of the sun, as one type, may arrive on Earth as another. This flavor changing baffled physicists, because it implied neutrinos must have mass, however tiny, defying the standard model of particle physics. Above and below, the ghost particles are shapeshifters, slipping identities as easily as shadows shift with the light. You drift in imagination into the sun's core. Nuclear fusion blazes, fusing hydrogen into helium, releasing photons that will take tens of thousands of years to wander outward. But the neutrinos, tiny ghosts, depart instantly, racing at near light speed. Within 8 minutes they pass the solar system's orbit, gliding through your body without notice. If you could see them, the sun would not merely shine, it would pour a river of ghostly particles, brighter in neutrinos than in light. Scientists still argue about the absolute mass of neutrinos. Experiments in Germany, Japan, and the United States chase tiny values, measured in fractions of electron volts. Are they heavy enough to influence cosmic structure? Do they explain part of the dark matter puzzle, or are they featherlight, too airy to matter on galactic scales? The arguments remain, and so do the experiments, patient and precise. Pause for a moment to imagine the soundscape of neutrinos. If their flow could be heard, it would not be a roar or a hum, but a constant hush, a steady whisper like wind through reeds. It would never cease, never falter, always there, gentle and unnoticed. You breathe in, and the neutrino wind flows through you. You breathe out, and it continues unchanged. Above and below, you are wrapped in its quiet persistence. Here is a fringe tidbit. Some cosmologists suggest that the universe is filled not only with solar and stellar neutrinos, but with a cosmic neutrino background, relics from the first seconds after the Big Bang. These primordial neutrinos are colder now, almost impossible to detect, but if measured, they would confirm our deepest models of creation. Instruments like Ptolemy are being designed to attempt this impossible catch, to net the oldest ghosts in the universe. If successful, we would hold fossils not of stars but of time itself. Think again of Earth's history. For billions of years, neutrinos have poured through its crust and oceans, silent, indifferent. They have passed through every creature, every mountain, every river. They are universal witnesses, always present, never touched. In ancient caves, when humans painted animals by torchlight, neutrinos streamed through their walls. When pyramids rose, when glaciers melted, when your ancestors breathed, the ghost wind flowed on. Above and below, neutrinos bind history together as much as light or matter. You float in imagination into a detector, one of the vast underground chambers where scientists wait for the rare moment a neutrino interacts. Giant tanks of water, or liquid scintillator, rest in silence, surrounded by photomultiplier tubes. On rare occasions, a neutrino strikes an atom, creating a faint flash of light, like a single firefly in a cathedral of darkness. Most pass through without a trace. It is patience turned into architecture, waiting years for a handful of glimmers. Scientists still argue whether there are sterile neutrinos, an even more ghostly type that interacts only through gravity. If true, sterile neutrinos could solve puzzles of dark matter, bridging the gap between ghost particles and galactic structure. If false, then neutrinos remain what they are: light, elusive, fascinating, but insufficient to explain cosmic mysteries. The debate lingers, unresolved but fruitful. You pause in their presence, letting the quiet weight of their abundance settle on you. You are surrounded, penetrated, carried by neutrinos always. They are above you, below you, within you, unstoppable. Yet they do not harm, they do not burn, they do not crush. They are the gentlest messengers of the cosmos, evidence that the universe is not only violent but delicate, filled with streams that pass unnoticed. Your eyelids grow heavier, the neutrino wind becomes a lullaby, steady, endless. Above and below the solar system, the ghosts flow, indifferent yet eternal, shaping no destiny but singing of constancy. You drift with them, calmed by their invisibility, reassured by their presence. And as you breathe, the river of ghosts continues, unfelt yet undeniable, carrying the memory of stars and the first seconds of creation. The ghost wind of neutrinos fades into stillness, and you drift once more into the immense hush above and below the solar system. You have passed through stars and filaments, voids and attractors, cold spots and hidden currents. You have felt the hum of dark matter, the swell of dark energy, the murmur of gravitational waves, the whisper of neutrinos. And now, as your journey nears its close, you step back to take in the whole picture, the solar system itself suspended in an ocean of structure and silence, belonging to a universe both infinite in scope and intimate in presence. From this vantage, the sun is not the center but a lantern, one among billions. The planets circle faithfully, tiny beads on a cosmic string, each one familiar and fragile. Earth glimmers faintly, its blue atmosphere like a sigh against the dark. You remember, with a quiet smile, that you probably wouldn't survive outside this cradle of air and warmth. But here in imagination, you float safely, embraced by the universe itself. A historical fact centers your thoughts. In 1610, Galileo lifted his telescope toward the sky and saw Jupiter's moons circling their planet. It was proof that Earth was not unique, not fixed, but part of a greater order. 4 centuries later, your own gaze stretches far beyond, and yet the lesson is the same. Earth is not the center. The solar system is not alone. It is woven into a grand design, above and below. Now for a quirky note. Some astronomers affectionately call the solar system a local bubble, because our neighborhood in the Milky Way is carved by ancient supernovae. The sun drifts in a cavity of hot plasma, surrounded by shells of gas and dust blown outward long ago. Even at home, even on the smallest scales, you are floating within bubbles, structures shaped by explosions older than human memory. Scientists still argue about the universe's ultimate fate. Will dark energy stretch it forever, leaving galaxies isolated in the darkness? Will some new physics intervene, reversing expansion into a collapse? Or will space-time itself fragment into pockets, birthing other universes we will never see? Above and below, the possibilities remain open, and the arguments continue like gentle tides. You hover, listening to the soundscape of everything. The hum of dark matter scaffolds, the bass of dark energy expansion, the chirps of black hole mergers, the whisper of neutrinos, all merge into a single lullaby. It is the music of the universe itself, layered, infinite, yet calming. You realize that you are part of it. Your breath sinks to its rhythm. Here is a fringe tidbit. Some philosophers speculate that consciousness itself may be linked to the fabric of the cosmos, that awareness is not only a product of brains, but of the deep order of reality. It is speculative, unprovable, perhaps fanciful, but it reminds you that even in imagination, you are woven into the same fabric you observe. Above and below, within and without, the divisions blur. Think again of history. Humans once told stories of heavens above and underworlds below. Today those myths are replaced by galaxies and voids, particles and waves. Yet the feeling is the same: wonder at what lies beyond reach, awe at being small but included. The difference now is that science gives detailed data, evidence, but still leaves space for mystery. Hover a moment longer. The solar system glimmers in the Milky Way, itself a bead in Laniakea, itself a strand in the cosmic web, itself a ripple in expanding space. Above and below are not boundaries, but continuations, endless layers of belonging. You are never lost, you are always part of something greater. Your eyelids grow heavy. The cosmos cradles you, the great attractors pull, the voids yawn, the filaments glow, and you drift gently among them, rocked by the knowledge that the universe is vast yet intimate, strange yet soothing. Scientists still argue, but you do not need certainty tonight. You need only the rhythm of questions, the comfort of scale, the reminder that you are held in a universe far larger than fear. And so above and below the solar system, you rest within mystery, within music, within belonging. The journey slows now. The lights of galaxies dim, the filaments dissolve into haze, and the music of space-time softens into silence. You feel yourself returning, not to an edge but to a calm center within. Your breath deepens, your body grows heavy, your mind begins to loosen its grip on thought. You remember the wonders you passed, the rivers of galaxies flowing into Laniakea, the whispers of dark matter scaffolding, the quiet acceleration of dark energy stretching space. You remember the anomalies, the cold spot, the ghost particles, the rippling waves of space-time. Each one was strange, each one unresolved, yet together they were a lullaby of curiosity, a reminder that mystery itself is gentle when held without fear. The solar system surrounds you again. The sun burns steadily, planets circle slowly, Earth cradles you with its fragile atmosphere. The immensity of what lies above and below no longer overwhelms, it soothes. You know you are part of it, not separate, not excluded. The universe carries you as surely as gravity holds you to your bed. Let that thought settle. Every galaxy flows, every wave passes, every particle drifts, and so do you. The same rhythm guides them all. You are not lost, you are exactly where you should be. Breathe slowly, feel the calm rise within you. The night sky, once vast and daunting, now feels like a blanket, soft and endless, spread gently above. The galaxies glow faintly at its edges, and the hush of neutrinos flows through like a breeze. Close your eyes, let go. The universe will continue its song without you, for a while. It has for billions of years, and it will for billions more. For now it invites you to sleep. Good night.